Hello and welcome to another 10-minute tutorial. Today we're going to have the second part of our pH calculations, and we're going to focus on Kw and how to do pH calculations of strong bases. So Kw is the ionic product of water. Water dissociates into its ions according to this equation. And we could, like any weak acid, write a Ka for this expression, where we would have the concentration of H plus times the concentration of OH minus divided by the concentration of water. But of course the concentration of water is very large in comparison to H plus and OH minus concentrations, and we can actually consider it a constant. So we take it out of the equation and we end up with the expression for Kw. And you can see perhaps why it's called the ionic product now, because it's the product, i.e. the multiplication of the concentration of the two ions that make up water. Its all units will always be moles squared dm to the minus 6. There's important features to note about this constant. Obviously the concentration of H plus and OH minus is always the same. You can't have more H plus from water without getting any OH minus. The pH of pure water at 298 Kelvin is always 7.0. So that means the concentration of the hydrogen ions is 10 to the minus 7 moles per dm cubed. And of course the OH minus ions are the same concentration, and so therefore at 298 Kelvin the ionic product of water is 1 times 10 to the minus 14 moles squared dm to the minus 6. Of course we would have learned with equilibria that they are temperature dependent, and equilibrium law says that the equilibrium constant is constant at a given temperature. Of course, change the temperature, you change the position of the equilibrium. And so that's why I'm referring to Kw at 298 Kelvin. We should have a look and see what happens if we change the temperature of the water, and what that might have effect on the value of Kw, and of course therefore its pH. So what do we use the Kw for? Well, we need it to calculate the pH of strong bases. Strong bases fully dissociate in water and they release hydroxide ions. And so the H plus ions concentration, and obviously therefore the pH, is linked to the concentration of hydroxide ions through the Kw expression. And if we know the OH minus concentration, then we can work out the H plus concentration and therefore do the minus log of that and therefore work out the pH. So rearranging the equation for hydrogen ion concentration, it obviously equals Kw divided by the hydroxide ion concentration. I tend to prefer to use pKw when doing base calculations. If we take the value or the expression for Kw, hydrogen ion concentration times hydroxide concentration, and now take the minus log of everything to get the pKw, we'll get the minus log of H plus the minus log of the hydroxide ions concentration, and perhaps you can see now that that gives us pKw. The negative log of hydrogen ions is pH, and the negative log of the hydroxide ions is pOH. So if Kw is 1 times 10 to the minus 14, pKw will equal 14. Therefore, pH equals 14 minus the pOH. Of course, this is only true at 298 Kelvin, where we'd have to have a different number for the 14 if we were using a different temperature. So let's look at a worked example. Let's take sodium hydroxide. Of course, it's a strong base, so it dissociates completely when in solution. And so we can say if the concentration of sodium hydroxide is 2 moles per dm cubed, then the concentration of the hydroxide ion is also 2 moles per dm cubed. Let's do the POH method. POH is minus the log of the OH concentration, which is negative log 2, which is negative 0.301. Put this into the rearranged pKw equation, and assuming we're at 298 Kelvin, we get 14 minus negative 0.301, which of course gives us a value to 1 decimal place of pH 14.3. When we were looking at strong acids, I was saying to be very careful to remember that some acids are diprotic and would release 2 H pluses for each acid molecule that dissociates. And a similar case can take place in strong bases. If we take barium hydroxide, of course when that undergoes to complete dissociation, 1 mole of barium hydroxide will produce 2 moles of hydroxide ions. Consequently then, if the concentration of barium hydroxide is 2 moles per dm cubed, then the concentration of hydroxide ions is 4 moles per dm cubed. Doing the POH method again, POH is negative log 4, which is negative 0.602. Put that into the rearranged pKw equation, and assuming we're at 298 Kelvin, we get 14 minus negative 0.602, which of course is 14.6 to 1 decimal place. I was saying, of course, that the equilibria are affected, the position of an equilibrium is affected by the temperature. So let's have a look at the dissociation of water. The forward reaction for this equilibrium must be endothermic because we're breaking the hydrogen-oxygen bond in the water, and breaking bonds requires energy. So the forward reaction, as I say, is endothermic. If you were to approach this in any kind of equilibrium law question on an exam, you would say that as the temperature of the water is increased, the forward reaction is favoured, the equilibrium moves to the right. It opposes the change. If the equilibrium is moving to the right, then the value of the equilibrium constant will increase. Of course, in this case, we're talking about the ionic product of water, Kw, so therefore that will increase. And of course, if the equilibrium is moving to the right, we end up with a greater concentration of hydrogen ions. So if a hydrogen ion concentration has gone up, then pH will have gone down. So warming water will cause a decrease in its pH. We can't say, and it's wrong to say, that the water becomes more acidic, because the production of H plus ions is comes along with the production of OH minus ions. So if the concentration of H plus ions increases, then of course the concentration of OH minus increases to the same extent. So the concentration of H plus and the concentration of OH minus is always the same. pH will decrease, pOH will decrease, but because H plus concentration and OH minus concentration are the same, water is still neutral. So by following this tutorial, you should now be able to write an expression for Kw. Use Kw to calculate the pH of strong bases. You can either use the rearranged Kw equation, or you can convert that to pKw. The exam questions will allow both ways. You understand that the dissociation of water is endothermic, and you can appreciate that the pH of water, and therefore bases, will be different at different temperatures. Anyway, go to my website, the link is in the description box below, and try some of my test yourself exercises. Find me on Facebook, follow me on Twitter, and subscribe to the YouTube channel for more 10-minute tutorials.